Alright, so we're going to start section 7.3. 7.3 is broke down into two parts. Alright, so this is part 1, introducing you to critical values and relative extrema, and then part 2 will be applications. Alright, so just like with one variable functions, where we found critical values, and then we determined if the critical values were relative max, relative mins, or neither max or min, just a critical value. We're going to do something very similar here with multivariable functions. Now, with multivariable functions, things get a little more complex because their pictures are a little more complex. They're multivariables. Again, we're going to stick with two variable functions, so our functions will be drawn in 3 dimensions. Now, we won't do any drawing in 3 dimensions, but that's what makes them more complex. Alright, so relative extrema definitions for multivariable functions are very similar to what we had in one variable functions. Alright, so a function f of xy is said to have a relative maximum at some point. So AB would represent my exit value and my y value. Alright, that would be the point. Alright, in the domain of my original function, if, when I plug that point in, it's bigger than all of the function values of f of x near that moment. Alright, so circular disk on that moment. Alright, the minimum's the same thing. Alright, if my function at the point CD, so CD would represent the x value and the y value, when I plug it into my function, it's smaller than all of the other values near that. And again, a circular disk means it's not over the entire function, it's just over near that value, right? Close to that value. Alright, I'm going to pop up a picture. Actually, I just Googled some 3Ds. There's some in your book too if you go look. Alright, but this would be an example of a 3-dimensional curve. Alright, so it's in 3 dimensions. There's a y, which would go up and down. There's the x, which goes left to right. And there's the z that would kind of come out of my page. And so, again, we'd look at this and see there's like peaks and valleys. Alright, so there's, in this particular one that I have graphed here, there's at least 3 relative maximums, right? That red edge and those 2 little yellow edges would be relative maximums. And then if you kind of look at it, it's hard to see. You can see one relative minimum, and there's probably another one back there. That's what we mean by in 3 dimensions. And so when we go and look at this, if I go take another picture, alright, so this would be an example of one where I've got a maximum. Alright, well, you flip that, you flip that around, alright, and you would have the minimum case, right? That would be an example of a minimum, alright, so minimum and then a maximum, alright, so in 3 dimensions though, so that's what makes this a little tougher, it's in 3 dimensions. Alright, so we're going to get to finding those. Alright, we're not going to graph them. You don't have to worry about graphing them. I just wanted to kind of show you some pictures so you understand the complexity of it. Alright, so we're going to be finding relative max and mins and eventually applying it, which means we're going to be finding absolutes. Alright, absolutes are using the same definition. It just means that it's the biggest function value, it's the biggest function value on the entire domain, or the smallest function value on the entire domain. Again, it's the same as the one variable case. We just have 2 variables we plug in our domain. Alright, so now how we find them. Alright, again, we can only have relative extrema at a point. The point would represent there's an x value and a y value, right? My x value is a, my y value is b. The point has to be in the domain of my original function. Alright, if a point is critical, alright, when do we get critical values? Remember, it's similar to the one variable case. In the one variable case, we got critical values at 2 outcomes. Either where my function has a stopping point, right, which has, again, a peak or a valley, or where it didn't exist, or something weird was going on. Now, in the multivariable functions, we're going to only look at the simple case where we have a stopping point. So we get a critical point when the function comes to a stop. Now, the difference here with multivariable functions is it stops. Alright, we have to stop in 2 directions. Alright, there's an x direction and a y direction. So in order to get that mountain-like shape, or the valley-like shape, again, it's 3 dimensions, that's what that sort of circle is. Alright, it's got to stop in 2 directions. Alright, so it's got to stop in the xy direction. Alright, and so again, that's what we're going to be looking for. There's got to be horizontal tangents. Actually, it has more to do with a horizontal plane. Alright, that'd be a horizontal plane. where we're going to find where my slope is 0, but it happens in 2 directions. Alright, so we still want to find a stopping point, a critical value. It's just a little more complex when we get to these multivariable functions. Alright, so the definition: a critical point of a function with 2 variables, like the one variable function, can only occur at values in the domain, and these are at the values where both first order derivatives are equal to 0. So both of my derivatives are equal to 0. Right? There's no change in the function with respect to either variable. There's no change with respect to x, and there's no change with respect to y at the same time. Right? There might be other places on the curve where x is not changing but y is. That's not a critical value. Excuse me, man. Meaning we have a point on f of x where the derivatives are 0, not changing, not increasing or decreasing in both directions. What this turns out to mean is we have to find where the partial derivatives are 0 at the same time. Alright, so we need to find an x and y, which is my point A, B, that make both equations true. My first order derivative with respect to x is equal to 0, and my first order derivative with respect to y is true. Alright, when that's true, then that point A is a critical point of my function. Alright, well, what that means, guys, is that we are going to have to solve systems of equations with 2 variables. Alright, so I've got to solve the system where my 2 partial derivatives equal 0, and I need to find the point x and y that makes both of those true. Alright, I am going to add a case to then what's in the notes. There are 2 sort of algebraic processes, and there's one kind of special case. Alright, so first, you can solve by substitution. Alright, you should know what substitution is somewhere in your algebra history. They should have talked about solving systems of equations by substitution. Alright, I am going to recall it here for you, and we will practice it in an example. Alright, so remember the substitution method is you pick one equation and solve for one of the variables. So you pick one of the 2 equations, one of the 2 partial derivatives, and either pick x or y to solve for. And sometimes there's an easier function, sometimes there's not. Once you've solved for the variable, so you can solve for x equals some expression of y, you take that function, the expression of y, replace the x value in the other derivative, right, the other equation, and then you should have an equation with just one variable, and you solve for that one variable. And again, like I said, when we get to the examples, I'll do an example of where we'll do this. And again, it should be something you remember from algebra. Alright, the other 2 cases, so again, I added a third case. The second case, which in a lot of our applications will work, is if my first order derivatives come out linear. Alright, first order derivatives come out linear, meaning I can put them in a linear form, the standard form for a line, some number times x plus some number times y equals a constant. Right, usually, and we'll do an example of this, and I'll remind you how to solve matrices on your calculator. You can only use matrices, though, if it's linear, if you can write it in that form. If you can't, you have to use the substitution method. Right, then you'll plug it into your calculator and solve using the row-reduced echelon form. The x value and the y value that comes out will be your critical point. Alright, this last one, which I'm adding to your notes, is sort of, again, another special case. And actually our first example in the next set of notes will be this case. If, when you find your first order derivatives, alright, so you find the first order derivative with respect to x, you find the first order derivative with respect to y, set them equal to 0, well, if each of those equations only has one type of variable in it, so usually it's the f of x has only x values, the f sub y only has y values, alright? And so you just solve them accordingly. You set them equal to 0, and you solve the f sub x set equal to 0 for x, and you solve the f sub y set equal to 0, solve for y. Alright, so you treat each equation separately. Alright, and I will do a couple of examples in class, because none of the equations have both x and y terms. So again, this works when that's the case. Alright, so we're going to get to solving that, and that'll be the next set of notes. Alright, so that was just kind of talking about where they're having. Now we're actually going to go through the methods and solve some, and that'll be the next set of notes.